Okay, we're off to chapter 9 as we finished, I think, chapter 8 last time, which was gases. So in chapter 9, we're going to talk about obviously the liquid state. We're going to talk a little bit about intermolecular forces, and we'll talk a little bit about solid, I think, towards the end as well. So let's start with sort of intermolecular forces. And intermolecular forces are the forces, basically attraction between two molecules. It's basically how one molecule basically interacts with another molecule. And it can be two molecules that are the same molecule. It could be two different molecules, how they interact with each other. But it is that attracted force between them. These intermolecular forces are responsible for things like boiling points, melting points, how high or low, for example, you might have in those things. Also responsible, for example, for, the major sort of state that you would find perhaps these guys in. If you have something that has a really weak intermolecular force, it's most likely going to be in the gas phase or be able to go into the gas phase really easily. Something with a stronger sort of intermolecular force will probably stay more towards the solid or liquid. All intermolecular forces are essentially the same interaction. So they are all this basic interaction between molecules of pretty much the negative side of one molecule is going to be attracted to the positive side of another. And that's how all intermolecular forces pretty much work is, you got a positive side and a negative side electrostatic attraction between them. So for example, this is the force like if we had two water molecules together. And if two water molecules together, because water is polar, positive side closer to the hydrogens, negative side closer to the oxygens. So when these water molecules come together, they bond to each other through the negative side of one water molecule to the positive side of another. As we'll talk about here in this chapter, that is what is known as hydrogen bonding, which is actually a relatively strong intermolecular force. But that is the force that holds this entire sort of water molecule together with this entire water molecule is that force that basically holds those guys together. Now, again, like I said, the strength of those type of forces do play a very big role in terms of boiling points, melting points. The stronger this sort of force is that holds these molecules together, the higher the amount of energy you would need, for example, to break those guys apart. And that translates to a higher melting point, boiling point type of temperature because you got to put a lot of energy in there. Now, the weaker that sort of force, again, between two molecules, the less energy you got to put in there. And what that basically relates to is a much lower temperature in terms of boiling points or melting points. Now, intermolecular forces are different than intramolecular forces. Intramolecular forces are actually the forces within the actual sort of molecule itself. It is the force that just holds like one molecule together without it falling apart into pieces. That is essentially like your ionic bonding if you're dealing with an ionic compound, and also your covalent bonding, your sharing of electrons if you're dealing with more of a molecular sort of compound. So, for example, if we take just one water molecule. It is, in terms of the intramolecular force, it is those bonds there between the oxygen and hydrogen on each side. It is the sharing of electrons between them. And again, that intramolecular force means within the molecule. And again, it's basically the forces that hold that together. Pretty much when you're comparing intermolecular forces and intramolecular forces, intramolecular forces like ionic bonding, electrostatic attraction, covalent bonding is going to be much stronger than any intermolecular force. Once again, we know that just from, again, practical application of life. We have over our years probably heated up water, I imagine, maybe in chemistry lab, maybe in the kitchen. And when you do heat up water and you get it to like 100 degrees Celsius where it normally will start to boil, the bond that actually breaks first is, again, this bond between the different water molecules. And what that allows, for example, if this was water in its liquid state, it will allow these two water molecules basically to separate out from each other and, for example, go into the gas phase and make water vapor or steam at that point. Now, if it was opposite and the intramolecular forces were weaker than the intermolecular forces, what that would mean is when you would go heat something like water, you would actually break these bonds first, and that would create like hydrogen gas and oxygen gas, which is not a good thing. And we know that doesn't happen. Obviously, again, when we heat water, we basically get steam, which is still water molecules. So we didn't break them apart into their elements or anything like that. So this doesn't happen. And again, that's a prime example of why intramolecular forces are, again, much stronger than the intermolecular forces. Any questions on that there? Yep. So we're going to talk mainly about intermolecular forces here and some different types of intermolecular forces. So intermolecular forces is really what we're talking about. And again, those are our forces between molecules. And the first type of intermolecular force that we're going to talk about is what is referred to as dipole-dipole forces. And dipole-dipole forces are, if you remember, happens pretty much for our polar molecules. So these are pretty much your main type of intermolecular force that you're going to have when you get basically two polar molecules together. These could be polar molecules that are the same thing. These could be two different polar molecules. But when you get two polar molecules together, you'll get this dipole-dipole interaction. And these are typically polar molecules that cannot hydrogen bond, and we'll talk about what can hydrogen bond later. But these are also polar molecules that cannot. You may remember that basically the definition of a polar molecule is unequal sharing of electrons overall in the molecule, and it has our favorite thing, which is a dipole moment, right? And dipole moment is really where this name comes from. Dipole-dipole, basically two polar molecules. This is the main force for polar molecules because they are polar, which means no matter what you do to them, they pretty much are always ready to interact like this because they will always have a side that's more positive. They will always have a side that's more negative because of the unequal sharing of electrons. They don't have to wait for anything to happen to allow them to sort of do that. They're good to go out of the box. They got a positive side and negative side, which means they're good to interact with one another. Basically, it is what I was talking about earlier. It is the polar side molecule of one and the negative side of the other polar molecule will again basically be attracted to each other. And that is how they're going to interact with each other. And that's what's referred to again as dipole-dipole forces. Now, when we get all these sort of molecules to come together, for example, in the liquid phase and even in the solid phase, especially in the solid phase, as they kind of slow down, they lose a lot of energy, right, to come into the solid phase. What they really try to do is, because they're going to be really close to one another, they try to maximize that attractive forces between the positive side of one molecule and the negative side of another. And they try to really minimize where they get kind of negative sides near negative sides or positive sides near positive sides, because they will not want to be near each other like that. They will be repulsed by each other. So essentially what will happen is they will kind of keep moving around, kind of wiggling around and moving around until they kind of find what they consider sort of the optimal arrangement where they have been able to pretty much maximize those attractive forces between the opposite charges and also minimize those similar charges being near each other. And it actually reduces down the overall energy when they do that, as they kind of move around and align themselves up like that. And that's what we see here again. We got our basic dipole-dipole interaction, opposites attract. And when we get a bunch of them together, again, they're going to try to maximize that opposite attraction, but again, kind of move themselves around to minimize negatives near negatives or positives near positives. But no matter what you do, they are going to kind of be near each other, but they will kind of keep moving around until they sort of feel comfortable in terms of the arrangement, and where it really does sort of maximize more of the attractive forces than the repulsion type forces. Another type of intermolecular force is what is referred to as an ion-dipole force. And it is pretty much what the name sounds like. Ion is an ion, yeah. So either a cation or an anion. And dipole is typically a polar molecule. So ion dipoles are between ions and polar molecules. The strength depends on the charge and size of the ion and the dipole. For equal charges, the more strongly the anion is attracted. The cations are usually smaller than the anions. Ionic compounds usually have low solubility in nonpolar solvents, and that is because when you put something that's ionic in, it has really no way, as we'll talk about, to kind of interact well with something that's nonpolar. Because as we'll talk about, basically, if you're nonpolar, you're kind of neutral. You don't have a positive side, you don't have a negative side. You have equal sharing of electrons over the entire molecule. So there really is no charges that allows you to interact with other molecules. By the way, ion dipole is essentially what happens, for example, when you take like sodium chloride and you go dissolve it in water, right? So this is a ionic compound, and that's a polar compound. And what will happen is essentially the sodium ions, which are positively charged, will get attracted or be surrounded by water, negative side, which is the oxygen in this case. And there you have a polar molecule attracted to an ion, and this is ion dipole. Same thing happens with the chloride ions as they're floating around. They, though, are negatively charged, which means they're actually attracted to the positive side there of water, which would be the hydrogen in this case. And that, again, is essentially how you dissolve basically an ionic compound in something like water. They're able to interact with each other, really still basically based off of the sort of opposite attraction that's there between the ion and either the negative side of water or the positive side of water. This is also why when you try to drop something like sodium chloride into a non-polar solvent other than water, for example, which is polar, you end up with this non-polar molecule, which again is pretty much neutral. It has no charge. So it has really no good way to maintain interaction with those ions. And that's why they really won't mix or dissolve really in there. You'll still be able to see them. So if you took something like sodium chloride and put it into something like hexane, which is a non-polar solvent, you can mix that all day. The crystal basically is just going to hang out there because the hexane is nonpolar. It's not going to be able to really interact with that ionic compound. And again, it's really because this nonpolar guy is neutral, no charge. These guys have charges, so they want to interact. So as we might have talked about previously, and we will see probably in this chapter, maybe the next one, but essentially that is the way that things sort of interact with each other in terms of solubility. And intermolecular forces plays a really big role in terms of solubility. And if something is going to sort of mix with something else or dissolve in something else, basically they both need to be using kind of the same intermolecular forces. So they want to be using the same intermolecular forces that they use with themselves. And if they are, then they're going to be a pretty good match because it's just going to be natural for them to mix because they're all using the same type of interaction. When you get two things, for example, like our sodium chloride there and a nonpolar guy, they're using very, very different ways of interacting, and they're just not going to really be able to interact with each other because they're both trying to do something different, basically, and they can't maintain that interaction. So speaking of nonpolar guys are typically the main type of interaction that you have with nonpolar guys is dispersion forces. So dispersion forces is pretty much your main and only way for nonpolar molecules basically to interact. And in terms of dispersion forces, although it is really the main and only type of way that nonpolar molecules interact, Really everything can do dispersion forces. Polar molecules could do it as well, but it's not their main way that they interact with things. So although they can kind of do it, that's not really the main way they do it. But this is really the main way here for nonpolar molecules. Again, how nonpolar molecules interact with themselves or other nonpolar molecules. So this is the way they interact with each other. Now, the problem with nonpolar molecules, as I just mentioned a second ago, is they are neutral, basically. There is no charge that happens with a nonpolar molecule because of that equal sharing of electrons that are happening. So it needs essentially something to occur to it to allow it to kind of temporarily gain a charge. So in order for this guy to sort of interact, it almost needs something to happen to it. And when something does happen, what it will allow that nonpolar molecule to do is temporarily gain some charges, get some separation of charge. But otherwise, it can't really do too much there. So what are some things that can kind of make that happen? These are sometimes referred to as induced dipoles. And what that means is basically under normal conditions, it has no positive or negative side. But when something happens to that nonpolar molecule, it creates again temporarily a positive side and a negative side, and that's a dipole, and that's what's known as an induced dipole because it normally doesn't have that. It has to have something happen to cause it to get a dipole sort of moment, if you will, temporarily. So there's two ways you could do that. There is ion-induced dipole. So essentially, if you did have a neutral molecule like we see down there that has no charge, and honestly, you roll up to it a positively charged ion, opposites are still going to attract in this case. And this neutral guy has electrons, and those electrons in it will then be attracted towards the positive ion, right? Again, opposites attract. And what that's going to cause is in that normal nonpolar molecule, it will temporarily cause this nonpolar guy to develop a separation of charge because basically all the electrons are heading to the left in my picture here. And that's going to cause a buildup of negative charge on the left-hand side of the molecule that normally is not there. Just happens to be induced by that positive ion coming by and floating by. That then would allow, obviously, in this case, some attraction to occur between those two guys that normally wouldn't. What happens when that ion floats away? There goes the attraction, there goes the separation of electrons, and just like this, not really, but it pops back to its nonpolarness there, and obviously it can't maintain that interaction. So again, it induces that dipole moment, gives it a way to sort of interact for a bit, but again, as it moves away, it's not going to be able to maintain that over the long period of time. Same thing would happen if you kind of backed in or moved in a polar molecule here next to a nonpolar guy. And that is what is referred to as dipole-induced dipole. So when you put that polar molecule next to that nonpolar guy, same idea is going to happen here if this was now the polar molecule with the positive and negative side. Again, going to allow those electrons to be separated. And now we have our polar molecule attracted to our nonpolar guy temporarily. Again, these are temporarily because as things start to move around and shift, they won't be able to maintain that separation of charge in the nonpolar molecule. Things will kind of go back to normal. Just an example, of that, just think about it sort of is like if you took oil and vinegar salad dressing, right? Oil is nonpolar, vinegar is polar, and you mix it up, right? It mixes, everything's nice and mixed, but when you put the bottle down on the table and just leave it alone, what ends up happening is everybody separates out. And that's again because over the long period of time, they can't maintain that interaction. And even though, again, polar molecules or ions can kind of do dispersion forces as well, it's really the nonpolar guys that's problematic there. It can't maintain that interaction. And that is one of the major difference between like nonpolar molecules and why they're so weak, for example, these dispersion forces is because they do have to rely upon something happening to give them those charges. And that's very different than what happens with a polar molecule, as I was talking about earlier. If you have a polar molecule, no matter what you do to that, the electrons aren't shifting back. They're just going to stay where they're at. And they always have a positive and negative attraction, which means they're good to go right out of the gate. They're good to keep that interaction. There's nothing going to cause those electrons to kind of move back away. They will always have that positive and negative attraction. And that's why dipole-dipole interaction is a much stronger intermolecular force than, say, dispersion forces, because they're always good to go and you can move them around or whatever you want to do with them. They both will have those polar molecules, will always have those charges that allows them to continue to keep that interaction going, as opposed to something like this, where again, if like the ion kind of moves away a little bit, those electrons in the nonpolar guy can kind of bounce back and it's going to go back to kind of being neutral in that sense. It has to rely upon somebody else coming by again to kind of cause that shifting that occurs. Any questions on that there? Now, this is one way that you can kind of get dispersion forces that occur. But what happens if you're not really dealing with like a polar molecule, or you have any type of ion that's present, and we're just talking about kind of nonpolar molecules and nonpolar molecules come together? Well, there's another way that you could kind of have this occur, and this is what is sometimes referred to as polarizability. And polarizability is the ease at which electrons in a nonpolar molecule can just decide to all vacation together on one side of the molecule versus the other. So in this type of situation, when you actually have kind of two nonpolar molecules together or near each other, what can happen in one of those nonpolar molecules is all the electrons, for example, because they're flying around, could just randomly decide we're all just going to go like over here to the right-hand side of this molecule. We're just all, a good majority of them are going to fly over to kind of the right-hand side of the molecule. That will then temporarily create a charge separation in this nonpolar molecule, which if this guy is next to this other nonpolar molecule, because now we have the negative side over here, this guy's electrons are going to go, we need to get away from that because that's negative. So they're going to go to the other side of that molecule. And now before you know it, two nonpolar molecules that did not have any charges will now temporarily gain some charges. And now, lo and behold, these two nonpolar guys can now interact with each other. Again, these are going to sort of come together, break apart, form some new interactions happening. And again, if those electrons kind of shift back, that little interaction is going to kind of break apart and again has to rely upon perhaps some more electrons shifting out and stuff like that. So the ease at which electrons are distributed or distorted is known as polarizability. And this is what is sometimes referred to as an instantaneous dipole. It just sort of happens because, again, all those electrons kind of head in one direction versus the other. Now, the larger the number, the larger the molar mass. So when you're kind of comparing dispersion forces, and you're kind of comparing between two different nonpolar molecules in terms of them interacting, say, with themselves, for example. The strength of this sort of dispersion force is related to molar mass. And typically speaking, the greater the molar mass, the stronger the dispersion force is. So the reason for that is the higher the molar mass means that you most likely have more atoms present, and more atoms would also bring more electrons. So there's a greater chance of those electrons now, because there's a lot more of them kind of moving around and coming in one place or the next. It also gives, with a lot more electrons in this sort of nonpolar molecule, more places for interactions to occur. So everywhere there's kind of those more atoms or elements present, they'll have more electrons and more interactions to occur. So if you have to compare, for example, between two nonpolar molecules and you want to know, for example, which one might have the higher boiling point between two nonpolar molecules, the one that would have the higher boiling point would be typically the one that is higher in molar mass. Again, because of that, more electrons, more interactions, even though it's a super weak type of force, that will allow them to basically interact a little bit tighter than something that is smaller, less electrons, less chance of them kind of going one way or the other. And again, you're going to have a weaker sort of interaction. Neither one of them is anywhere near what you would have with, say, somebody doing dipole-dipole in a polar type of interaction. But if you have to compare sort of nonpolar guys, that's basically what would happen. Now, when we talk about dispersion forces, like I said, it is basically the main force for nonpolar molecules. And that's why, for example, if we just take something like methane here, which is CH4, CH4 is a nonpolar molecule. Carbon, hydrogen is nonpolar. That's also symmetrical geometry, which means it's nonpolar as well. This guy's going to use dispersion forces, which is, again, relatively weakest type of force you could have, basically, in terms of intermolecular forces. That is why we typically find methane coming out of the gas vent, right? Like we're going to do later today, right? And it's typically a gas. Also, why a lot of nonpolar organic molecules are gases, things like propane, butane. They're held together by these very weak dispersion forces, which means you just look at them wrong and they're just going to kind of break away from each other and they'll be in the gas phase. Normally, they may be in the gas phase. That's also why, again, a lot of organic compounds that are liquids can very easily go from the liquid state into the gas state, and they're known as being volatile because, again, they're held together by these really weak dispersion forces. That's, again, why they throw you in a fume hood when you work in organic chemistry, so you hope we don't smell any of those bad vapors. And they're also usually very flammable, those vapors, so they want to make sure there's no Bunsen burners around. So as I mentioned before, the attractive forces that arise between these temporary dipoles are what are known as dispersion forces. And as I said before, basically the strength of this weak intermolecular force does increase with molar mass. Again, just the presence of more electrons allows us to do it. When we talk about dipole-dipole interaction, dipole-induced dipole, and dispersion forces, these are sometimes referred to, our friend, as van der Waals forces, as we saw with the van der Waals equation at the end of the gas chapter, where he took into account intermolecular forces and how gas molecules and gas molecules interact with each other. Now, when we talk about intermolecular forces, here is, again, some pictures of that instantaneous dipole. Normally, these two guys do not have a charge because they're nonpolar. This guy temporarily gains a charge, going to cause the second guy to temporarily gain charges. And now we have a way for these guys to, again, interact with each other. Now, the last type of intermolecular force that we want to talk about is hydrogen bonding. And hydrogen bonding is the main molecular force, intermolecular force for polar molecules. Now, these are polar molecules that have the ability to hydrogen bond. So if you have a polar molecule that has the ability to hydrogen bond, that is the type of intermolecular force it's going to use. Even though technically speaking, hydrogen bonding is really a type of dipole-dipole interaction, but it is sort of a special category onto itself, and that's known as hydrogen bonding. Now, what makes something able to hydrogen bond? Well, clearly you need a hydrogen, right? And you need a hydrogen that is bonded to a nitrogen, oxygen, or fluorine, which, again, if you look at the periodic table, that's upper right of the periodic table. That is our kind of three pretty heavily electronegative atoms, right? And when it hooks up with hydrogen, because those guys are fairly strong electronegative, you're going to get a really good separation of charge, and that's going to create that positive negative side that's really attraction, that's needed for that attraction. That, by the way, is what we see here with water. Here we have a hydrogen bond directly to an oxygen, actually on either side there. That's going to create, again, this pretty polar bond. And that's going to allow, again, one water molecule to interact well with another through opposite attraction there, which is our hydrogen bonding. By the way, that would also allow, and why, for example, things are soluble in water, say something like methanol here. Methanol actually has the exact same group there, OH, on it. And that would be positive, that will be negative, negative and positive. Once again here, they could hydrogen bond with each other, and that's going to make them really soluble in each other. So if you take methanol, ethanol, or even 2-propanol or 1-propanol, and these alcohols here, because they contain that OH group and they're relatively small, that will allow it to interact well with water, which is why it will do that. By the way, though, if you do get a lot of carbons, somewhere in the neighborhood of like 4 or 5 carbons with an OH group, they're not very soluble at all, actually, in water. And that's for a different reason. But what happens, for example, if you take like an alcohol that has just a ton of carbons there, all these guys with hydrogens, basically. And even though this guy, for example, here, will have the OH here, which is still polar. So it has this polar part, but the problem here is it has this really big non-polar part. So this part over here where all the carbons and hydrogens are non-polar. So even though it can sort of interact with water, frankly, this part of the molecule is too big and it gets in the way. It's sometimes referred to as steric hindrance. Basically, it's just too big. Even though it has this little guy here, this big thing gets in the way of water being able to effectively get in there and interact with it. So even though it does have an OH group, it just kind of gets in the way and it can't basically interact, as we'll talk about in the next chapter, I think. But basically, in order to get something to be soluble or dissolve in water, you need to replace water and water interactions with similar type of interactions. Water is not a giant molecule, which means you don't want to put a giant molecule in there, especially if it only has one little part that could interact with it. It's not going to be really, really soluble. The opposite is true as well, though. If you were to like litter, for example, a molecule with a bunch of OH groups all over it, that would definitely increase the solubility with water, because everywhere there's an OH group, it's able to interact with water, and that makes it really soluble. That's why something like something like sugar there, right? It dissolves in water. Sugar is a relatively large molecule, but it is littered with OH groups all over it. So everywhere there's an OH group on sugar allows it to interact with water, and that's why when you put sugar in water, right, it dissolves with no problem, because it has all those extra kind of OH groups that helps with it interacting well with water. Now, just so we're clear, just because something does have a hydrogen, it does not mean that it can basically hydrogen bond. So as I drew up earlier, there our friend methane, although it does have a ton of hydrogens all over the place, each of these hydrogens are attached to carbon and not nitrogen, oxygen, or fluorine. So in order for something to have the ability to hydrogen bond, the hydrogen in that molecule has to be directly attached to one of those 3 elements. If it is not, then it cannot hydrogen bond, even though there's a ton of hydrogens present. You know, even back here, there's a ton of hydrogens present, but none of them have the ability to hydrogen bond because they're all nonpolar bonds and they're not attached to a nitrogen, oxygen, or fluorine in this case. Again, this guy here would use dispersion forces, right, as its main source. Any questions on that there? This is also why, as we will see, why water is more or less dense in its solid state than it is in its liquid state, because of these hydrogen bonding that occurs. It's relatively strong attraction. So when the water molecules, again, kind of lose energy, they can't get themselves super close to each other because of the hydrogen bonding, and it creates all this empty space between the different water molecules, and that's what lowers the density that we see in ice versus, say, liquid water. So when we talk about sort of the 3 types of intermolecular forces, or more types, but you know, we have basically on one end, we kind of have our hydrogen bonding, which again is a type of dipole-dipole interaction. That's going to be your strongest interaction in terms of intermolecular forces. So if you come across something that can hydrogen bond, these guys are going to have pretty high boiling points. They also will have pretty high melting points because they're kind of hooked together really strongly, which means in order to kind of get them apart from each other, you have to put in a good amount of energy to do so, and that's going to relate to a higher boiling point or melting point to do so. So obviously here, an example would be like our water there can hydrogen bond, right? Now we have dipole-dipole, which is really the next strongest. And again, this is going to be, and hydrogen bonding obviously is for our polar molecules that can hydrogen bond. Dipole-dipole is for our polar molecules that cannot hydrogen bond. So for example, here, if you lay up something like, say, I don't know, we'll go CHF3, right? So if you draw something like this, look something like this. This is a symmetrical geometry, right? That is tetrahedral. The problem here is they are not all the same on the outside, right? So even though in a symmetrical geometry, if they're all the same, it's non-polar. But in this case, this would be a polar molecule. Because of that, everything on the outside is not the same. So this guy would do a dipole-dipole interaction. Obviously here, you could probably imagine near the fluorine is going to be more negative in that compound. And towards the hydrogen part would be more positive. And that is what it's going to use. Even though, again, here it does have a hydrogen, it is not directly attached to a nitrogen, oxygen, or fluorine. On the last part here, we have sort of dispersion forces, which once again are your weakest of all these guys. And these are pretty much your nonpolar molecules are really the main way that nonpolar molecules, again, as we talked about, interact with themselves and other nonpolar molecules as well. These are the weakest because they're temporary. As we talked about, you basically need something to occur for it to interact. An example, for example, we could go, anything that's nonpolar, like N2, for example, right? So that is a nonpolar molecule. It would use something like that to interact with. Any questions on any of those? Yeah, I would say so. Truth be told, hydrogen bonding is a form of dipole-dipole, but it is sort of classified by itself, the hydrogen bonding. Ion-dipole and what was the other one we had there? Ion-dipole and dipole-induced dipole are. I'm sorry, ion-dipole would be here. Ion-dipole would be here, and then ion-induced dipole and dipole-induced dipole would be over here as well. Yeah, so ion-dipole would kind of fall into that category there with dipole-dipole and that sort of interaction. Yeah. And then those ones that induce the dipole, like an instantaneous dipole as well, would be under dispersion forces, those kind of weak ones. Yeah. Other questions on that? So if we had something like, let's take a look at some here, maybe. Let's say we had, say we had NH3. Let's say we had CO2. We'll do Cl2. Let's do SO2. So for each of these, what type of intermolecular force would they use with themselves, obviously? So NH3 and NH3 and CO2 and CO2 and Cl2 and SO2 as well. So what would they use with themselves? And we'll add one more. We'll do C2H6. Okay, so let's take a look. So really, if you're maybe not sure, just a quick sketch of a Lewis structure might be good. So if I quickly sketch this guy, I look something like this here. First off, this is the trigonal pyramid, right? An unsymmetrical geometry, and that is going to be a polar molecule, right? So that's going to be a polar molecule, which means basically it's going to do one of two things mainly, either dipole-dipole or hydrogen bonding. Can this guy hydrogen bond with itself? It can, because we do have a hydrogen that is bonded directly to a nitrogen. So this guy would do hydrogen bonding in this particular case. Question on that there. All right, so if we take a look at and obviously, this would be more negative side. This would be more positive side when it would do that. We take a look at CO2. We do a little quick sketch of it from our Lewis structure days here. Looks something like this. And this guy is obviously linear in terms of its geometry. It does have polar bonds, but because of that geometry, they're going to cancel each other out, as we talked about. And this is actually going to be a non-polar molecule, right? Which means really this guy's going to use dispersion forces, right? So again, even though it has polar bonds, it's nonpolar overall. So overall, it's sharing electrons equally. It's basically a neutral molecule, and it will need those dispersion forces. Over here, a little Cl2 action, gonna be pretty much the same idea, right? This is definitely nonpolar, which means this guy would need dispersion forces as well, right? That is also why, if you remember when we did that experiment way back when, dare I say experiment 3, was it? When we had those test tubes and we had, like, I think you guys use hexane maybe, or heptane, which is nonpolar. That is why we had our chlorine up in the top layer, right? Because nonpolar and nonpolar are going to mix really well. They're both using dispersion forces. That's why we had our ionic guys, if you remember, like our sodium bromide in the bottom water layer, right? A little ion-dipole interaction happening in the bottom layer, right? And that's why it's more soluble there in that bottom layer until perhaps maybe they switch places, right? Over here, SO2, we get a quick little sketch of that guy there, perhaps something like this. A little angular type of action, definitely gonna be polar in this case. Can this guy hydrogen bond itself? It cannot, it doesn't have a hydrogen, so that's problematic perhaps, right? So we need a hydrogen to do that. So this guy's going to have to go with a little dipole-dipole interaction, right? In terms of how it's going to interact in that particular case. Lastly here, we got ethane there. I think I studied organic once, a long time ago. Don't remember any of it, just say that. Like something like that. That's all carbons and hydrogens, so that's a nonpolar bond. And obviously the bond between carbon and carbon is also going to be nonpolar. So this entire thing is going to be basically a nonpolar molecule. That means it is going to have to go with dispersion forces. Any questions on how you determine that? And when you're asked that question like this, they're basically referring to how, basically, for example, NH3 would interact with another NH3 in this particular case. If they were talking about two different ones, they would give you two different ones, like if they had, say, NH3 and like methanol here. These guys would interact through, well, the NH3 is using, what did we say? Hydrogen bonding, yeah. And this guy here is methanol, which looks like this. Does methanol have the ability to hydrogen bond? It does. Yeah. So they both would be using hydrogen bonding. That would mean those two guys should be soluble in each other or insoluble. Should they mix or not mix? They definitely will mix because they're both coming in with hydrogen bonding. So they both are using the exact same type of force, and that's going to allow them to mix. Now, again, if you kind of did you did like the methanol there with like our ethane there, right? These two guys, one again is going to use hydrogen bonding. The ethane is going to use dispersion forces. Should those two mix? Those two are not going to really mix. Again, they're using very different types of intermolecular forces, which means they're not going to interact well with each other. Any questions on that? By the way, if you had a guess between methanol and ethane, which one should have the higher boiling point? Which one has the stronger intermolecular force? Is it hydrogen bonding or dispersion forces? Which one's stronger? Hydrogen bonding. So methanol, when it's with itself, will hydrogen bond with itself, which will create a much tighter and stronger bond than, say, ethane with itself. It's going to use that dispersion forces. So between the two, you would have to put a lot more energy into the methanol to get them apart from each other, which is what happens at the boiling point, right? The boiling point is when it goes from liquid to gas, right? So you got to get everybody away from each other. So it takes a lot more energy to do that. In the case of methanol, because it's hydrogen bonding, that would mean it would have a higher boiling point than, say, ethane, which only uses dispersion forces, which if you just sneeze at it, it will probably go apart, pretty relatively easy. It doesn't take a lot of energy to do so, and it will have a much lower boiling point. Any questions on any of that stuff there? Yeah. So let's talk a little bit more about the liquid state. So when we talk about the liquid state, obviously molecules are closer than they are in the gas state. So basically, typically for most compounds in the liquid state, they're relatively close to one another, the molecules. The difference between, say, the liquid state and the solid state is in the liquid state, they have enough energy still to basically start passing each other, right? And that's why liquids are fluid, right? They pour and they make a mess all over the place, right? If you spill them. And again, because they have enough energy to basically continue to move past one another, and that gives it that sort of more fluid sort of property. Then when they get into the solid state, they lose all of that energy and they just basically just lock down basically and not really moving all that much because there's not a lot of energy basically happening. So viscosity is basically the resistance of a liquid to flow. It is related based on intermolecular forces. Water has a low viscosity and motor oil has a high viscosity. When we talk about viscosity, it also increases with temperature. So when you increase the temperature, everybody gains a little bit more energy. That's going to allow them to start moving past each other a lot faster, and again, not going to be as viscous, right, as, say, something like motor oil, which is not moving as much and don't have as much energy. So a little bit thicker, if you will, in that sense. When we talk about water, there's some types of interactions that are important in terms of sort of how water interacts with certain things. Water, which again is a polar molecule. There are two types of forces that we talk about in terms of molecules and sort of how they interact either with themselves or other types of molecules. There's cohesive forces, which are the forces of attraction between two similar molecules. So cohesive forces are how like one molecule basically interacts with itself, another molecule of itself. So like in water, how water hydrogen bonds with another is a cohesive type force. Adhesive forces are the forces of attraction between different molecules. So for example, how a liquid interacts when you put it in like a glass tube, test tube, graduated cylinder, beaker, whatever it is. What happens when we put water or liquid into a glass tube, we get typically a meniscus that forms, right? And that meniscus forms because of the attraction between, say, the water molecules and the walls of the container. So the molecules in the glass, basically. And that attractive force actually in the case, for example, of water and most liquids that make a meniscus like this, the attractive force between water and actually the glass container is stronger than the attractive force between water and itself. So what ends up happening is we get a meniscus that basically does that. So the adhesive forces is actually stronger than the cohesive forces in this case. Not all substances are like that, as we'll see, I think, in a slide down the road, but we'll take a peek at it here as well. If you had mercury in a glass tube, mercury will actually go the opposite way. We'll actually have a meniscus that kind of goes like that. And that is because in the case of mercury, the attractive forces between mercury and itself is actually stronger than the attractive forces between mercury and the glass. So in this particular case, the cohesive forces are stronger than the adhesive forces. And we actually get an upside down meniscus in that particular case. Surface tension is another sort of property of sort of water and liquids. And that is basically the elastic tendency that we find on the surface of a liquid. Energy is needed to expand the liquid surface. If it is higher for liquids that have a greater intermolecular force. And that's why, for example, as it says there, you can sometimes like lay a paperclip down on some water and it will kind of just float there on it. Also why certain bugs can walk across water, right? Surface tension, they can use that as they walk across it. Now, why does that happen on the surface of a liquid? Well, if you take something like, for example, water, and you have a bunch of water molecules on the surface, or a water molecule on the surface, it has water molecules, around it, basically. And it's going to feel basically an attractive force to the water molecules to the left and right. It will also basically feel attractive forces to the water molecules below it. So you basically got this water molecule at the surface that's getting stretched sideways and also pulled down, right? So that's what sort of expands and makes the tension at the surface of the liquid. There's no pull upwards, right? Because there's nothing above it. So it's only feeling kind of sideways pulling and downwards pulling, and that's going to create basically the surface become a lot more tense or sort of tighter pulled, if you will. And that's different than if you looked at a water molecule that's below the surface. You have a water molecule below the surface, it's almost feeling kind of equal pulling in all directions. So you don't get it kind of pulled kind of two ways like you do at the surface there, left, right, and then kind of down in that particular case. And that's what we see here again, our water molecules at the surface getting pulled kind of down into the sides. Nothing happening here. That's going to make a pretty tight sort of surface there tension that's going to happen. You just think about, again, kind of pulling a rope this way, right? And also pulling it down. You'll kind of get that really tightness. Again, that water molecule in the middle is just going to kind of feel pulling from all directions or attractive forces from all directions. So you don't get that surface tension in the middle of water that happens there. Now, one way, for example, that you can actually reduce the surface tension of water is to use something like soap. And what soap essentially is a two-part molecule. Soap has pretty much, and I'll just draw it like a squiggly line here. And basically, my squiggle line there is they're all carbons and hydrogens, basically. So these are all carbons and hydrogens, basically. It's kind of line structure. And basically, soap has two parts. It has this part that's basically all carbons and hydrogens. So everything there's in the little up, down squiggle are carbons and hydrogens. That's definitely, as we've talked about, nonpolar. And that's basically the nonpolar part of soap. This part over here, which is basically from a carboxylic acid, which is an organic guy, that is what is sometimes referred to as the polar head of soap, while the nonpolar part sometimes referred to as the nonpolar tail of soap, basically. And that's what makes soap effective in its job, which is mainly we use it when we are dirty, right? And most dirt is nonpolar. which works really well for the nonpolar side of soap, because when you put soap on, the nonpolar part of soap will mix really well with your dirt. And what that will end up doing is, on the other side of it, kind of outside of the dirt, you will have the polar side of soap. So basically, the nonpolar side of soap will trap the dirt because it will mix really, really well with the nonpolar side of soap, and it mixes really well with the nonpolar dirt. It creates what is sometimes referred to as a micelle, where a bunch of soap molecules get in there and traps all the dirt in the middle. Arranges all the outside of this little trap, the polar part of soap. And that's really good because typically if you use soap, you usually wash it off with water, which is polar. And when you wash it off with water, it's going to be attracted, no problem, to the polar side of soap, which is on the outside. And the water will take the soap molecules that have your dirt trapped, and now you're clean. Good to know how soap works, I suppose, as well, right? And how it actually works. Now, when we wash our car, for example, we usually will put water on our car in most cases. And if you have a car that's nicely waxed and stuff like that, and wax is non-polar, you typically will see water start to bead, right? And that's again because they're not going to be able to interact with one another. Also, if you have an umbrella when it rains around here occasionally, right? And you got an umbrella going on your umbrella, typically the water will bead off of it as well because it's non-polar. So when you go to wash your car, you typically, after you wet it down there, you take some soap, put a little soapy water on it, right? And then you can actually see it when you soap up the car. You can almost see like everything in the water start to spread out, right? And that is because of the interaction between soap basically and water. Soap, because it has, again, this polar part, what it's able to do is actually get in between these water molecules. And that's what causes basically the soapy water to kind of spread out. When you kind of wash your car, you can kind of see that. Or dirty dishes in a sink, right? There used to have an old Dawn detergent type commercial that has this thing, and they put like a drop of it in there, and you can see everything in the sink, the water and everything just go whoosh, spread out because of that happens. And obviously we wash it and then we dry it, throw a little wax on there, right? So that when if it gets rained on again, it beads a little bit, right? And all that good stuff. So soap is able to, again, sort of spread out, like I said, those water molecules by getting in the way. Now, adhesive and cohesive forces, as I mentioned in the previous slide, is really responsible for the meniscus that we see. And depending on which one is stronger, that adhesive versus cohesive forces, as to really what type of meniscus you see. We do typically see, in most cases, the typical kind of U meniscus, and we read from the bottom. But as I mentioned before, you could have sort of mercury, where the attractive forces between mercury and itself is actually stronger than the glass, and you get these upwards meniscus where you'd actually read from the top of it. The reason we read from the bottom of the meniscus or the top, depending on which way it's going, is without those attractive forces, those guys on the sides would actually be down towards where the middle is, right? The middle is not really in contact with the walls of the container, and that's truly where the volume is, which is why we look for the meniscus. If you read it from where the top of it is, that's just a result of the attractive forces that's occurring between the glass container and the liquid. By the way, we can get liquid to sort of rise up in a small diameter sort of tube, and that's what's known as capillary action, right? It'll kind of suck itself up into this tube through that attractive forces, because the liquid, for example, if you have a really small capillary tube, looks something like that. And again, when you put it on a liquid, because the liquid is attracted to the glass, it will allow itself to sort of rise up into the little tube, and it'll kind of suck itself into the tube. Any questions on that there? Let's talk a little bit about vapor pressure. Vapor pressure is the tendency of a liquid to vaporize, and that is what is referred to again as sometimes being volatile. If a liquid is volatile, again, it means that it can really kind of go into the gas phase from the liquid phase relatively easy. Liquids in an open container will start to evaporate completely because air will diffuse away basically what is happening. At the surface of any liquid that you basically have liquid molecules jumping out of the liquid, and you got slower moving kind of vapor molecules above the liquid dropping back in. So you got this sort of exchange that occurs at the surface of any liquid. That is also why if you spill just a little bit of water, say on the bench, it will evaporate by itself because you'll have the rate of evaporation that's occurring in lots of locations. And then you will have your friend air that will push those guys away. And as it pushes them away, they're no longer available to come back into the liquid. And eventually it will start to evaporate basically on itself. Also, why if you take a liquid in an open container, right, it will also start to evaporate, but it'll take a little longer because you only have so many liquid molecules exposed to the surface. You have a lot more underneath. But the same process will occur because as those guys go up higher, they will get pushed away and none of them will start coming back. And eventually, if you leave it open, you'll start to see the liquid layer obviously start to drop. That's also why we sometimes, if we put a stopper on it, right? That should prevent a lot of evaporation from occurring because the stopper will prevent those guys to escape basically above the liquid. Now we do create pressure above the liquid because when these guys escape the liquid phase, they now become gases, right? And gases have pressure. And as these guys escape, you now have gas molecules basically above the liquid. And that's what's known as the vapor pressure of a liquid. And the vapor pressure is really high when we have really weak intermolecular forces, right? So if we have really weak intermolecular forces, that means they're just going to be able to escape the liquid really easily, and you're going to have a lot of gas molecules floating around or flying around above the liquid. So a lot of gas molecules that can escape the liquid easily will create lots of gas molecules, lots of collisions, lots of pressure, so a higher vapor pressure above it. Now, if you have a liquid that has a pretty strong intermolecular force, what that's going to mean is not a lot of them are going to escape the liquid part easily and go into the gas phase or the vapor phase above the liquid, which means in those situations, you would actually have less gas molecules kind of above the liquid. So less gas molecules above the liquid will result in less collisions, less pressure, and a lower vapor pressure. So if you have something that has a fairly good intermolecular force, you will probably have something that has a low vapor pressure. Again, something like water would have a low vapor pressure over it. But if you took something like ethane, methane, any type of organic guy that's nonpolar, those guys are going to very easily kind of escape from the liquid phase into the gas phase, and those guys would have a high vapor pressure. And again, while they're volatile is, if you don't have a lid on it, these gas molecules could then just escape, right? And basically you will go into the gas phase. And that's why if we look at a container here and we put a liquid into a container and decide to throw a stopper on it, when you first put the liquid into this container, you're going to have a big rate of evaporation happening. So pretty much all that liquid is going to start to evaporate. The problem is, as it starts to evaporate in this scenario, it cannot escape the flask because there's a stopper on it, which means the only other option for it is it's got to come back down the other way. And what you're going to start to get at some point is a rate of condensation, right? When a gas goes back into the liquid. At some point, you'll actually reach equilibrium, which is what's over here. And in this particular case, when you reach equilibrium, the rate of evaporation will equal the rate of condensation. And what you will notice if you actually compare the liquid volume before and after that occurs, you'll actually have a little less liquid than you started with because a lot of the liquid molecules have escaped and they're now flying above the liquid as gas molecules or vapor, causing vapor pressure, right, above that liquid. And again, because they're no longer in liquid phase, The little adjustment in the volume of the liquid actually goes down a little bit because now you got those guys out there flying around above the liquid. Any questions on that there?